Okay, in this video, let's talk about section 3.5. Graphing techniques, transformations. Okay, so let's first talk about the vertical and the horizontal shift. The example. So use the graph of fx equal to x squared to obtain the graph of gx equal to x squared plus 3. Okay, so let's check. Okay, so it's let's make the coordinate system. First, when x is 0, x is 0, f0, f0 is 0, x squared, and g0 is a 3. So f is here, and g is f is here, g is here. This is g of 0, 3. So 0. And 1 for 1. When x is 1, f1 is 1, and g1, 1 squared plus 3 is 4. It's here. If you get another one, the number will be slightly bigger. So when x is 2, f2 is 4, and g2 is 2 squared plus 3 is 7. So 2, 1, 2, 3, 4, 5, 6, 7. 7 is here. Right? So if you make enough sample, you will see it looks like this. And because if it's an even function, so the left branch is identical to the right branch image. Okay, so this is a graph, and the original graph is like this. The original graph is this one. Okay, so this is G, this is F. If we have the original graph of fx, we can imagine that in order to get a g of x, we actually shift from the graphs. We can see that if we shift 3 units up, vertically up. Shift the graph of fx 3 units up, we get the graph of g of x. So just directly shift it 3 units up, we will get the g of x. It's why we shift it 3 units up, because we add 3. You add 3. Okay? When you add 3, directly add 3, you shift the graph vertically up certain units. And the next example, if you have fx x squared gx x squared minus 4, you are asked to do the similar step. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7. And we make the same label. X is 0, then f0 is 0, and g of 0 is negative 4. 1, 2, 3, 4, negative 4. And when x is 1, f1 is 1, and g of 1 is 1 squared minus 4 is negative 3. When x is 2, f2 is 4, g of 2 is 2 squared minus 4 is 0. And here we can do one more thing. When x is 3, f3 is 9, and g of 3 is 9 minus 4 is 5. 3. 1, 2, 3, 4, 5 here. So you connected them smoothly. And you make the left branch symmetrically. Okay, so this is the graph of g of x. And the graph of the original function is, well, it's like this. The graph of fx. Inside is a graph of fx. And we can see that we shift the graph of fx vertically down 4 units. Then we obtain the graph of g of x. Okay, so again, it's vertical because you directly add a number. Down because you have minus sign. The minus sign give you the direction. You vertically move it vertically down. And the 4 unit comes from this quantity. The quantity is 4. The negative sign we already discussed, meaning it's a shift down. Okay, so to make this more precise, we have the conclusion. Those conclusions are on page 245. There's 2 boxes. If a positive real number k is added like this 3. The 3 is a positive k added to the output of a function y equal to fx, the graph of the new function y equal to fx plus k is the graph of f shifted vertically up k unit. Shift vertically up. So you see, these two words are important. It's vertically up, and it corresponds to a positive number added. If you add it to the fx, you get shift vertically up. Okay, that's the first conclusion. We have two conclusions. This first conclusion corresponds to the first example. And second conclusion, technically you almost copy the first conclusion, just change added to be subtracted, up to be down. Okay? Let's see. If a positive real number k is subtracted, if a positive real number k is subtracted from the output of a function y equal to fx, the graph of the new function y equal to fx minus k is the graph of f shifted vertically down k units. Okay, it's just subtracted, positive, down k. These two conclusions are parallel. One is addition, one is subtraction. One is up, one is down. Okay, so this is directly subtract or added to the output, directly subtracted and added to the output. Then you have a vertical movement. Vertical, we call it transformation, vertical transformation. Okay, after we talk about the vertical transformation, vertical, either up or down, technically we finish all both cases. Now let's talk about the horizontal shift. Use the graph of fx equal x squared to obtain the graph of gx equal to x minus 2 squared. Gx equal to x minus 2 squared. Okay, now let's check. We have a table. The units 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's just do the plotting. When x is 0, x is 0, f of 0 is 0, this point. G of 0, g of 0, well, x is 0, 0 minus 2 is what? Is a negative 2. Negative 2 squared is 4. G of 0 is 4. 1, 2, 3, 4 here. This is a point. And when x is a 1, f1 is 1. G of 1. G of 1. 1 minus 2 is negative 1. Negative 1 squared is a 1. G of 1 is 1. G of 1 is 1 here. Then when x is 2. When x is 2, f2 is 4. And the g of 2 is 2 minus 2 is 0. Squared is 0. G of 2 is here. Wow. Now let's make another example, another sample point. When x is negative 1, when x is negative 1, f of negative 1, negative 1 squared is still 1. So here we have the graph like this. This is a graph of g. You see 4, 1, 0, corresponding to 0, 1, 2. So this is a graph of g. And let's check what is a graph of f. When you get 0, you get a 0 here. When you get negative 1, you get 1 is here. If we get x equal to negative 2, f negative 2 is 4. Negative 2 squared is 4. Negative 2 squared is 4. This dotted line is a graph of f. You see? These two curves are identical. Just you shift it to the right side. You shift it to the right side 2 units. And if you continue this, let's check. When x is when this x is equal to 3, f3 is 9. It's already very big. And g3 is 3 minus 2 is 1. 1 squared is 1. 9. Can I draw 9? F1 is a 1. This is F1. F2 is a 4. 2 is a 4. F3 is a 9. 9 is a 5, 6, 7, 8. 5, 6, 7, 8, 9. 9 is here. And for G of 3, 3, 9 is here. G of 3 is a 1. G of 3 is a 1. 1 is here. And x equal to 4. Let's talk about G of 4. G of 4. 4 minus 2 is 2. 2 squared is 4. G of 4 is 2. Remember, this is a graph of G. And you see here, I just pick up the value from 0 to 4. These 4 values, 5 values. This graph is exactly the graph of y equal to x squared, but you just shift it to the right, horizontally shift right 2 units. Okay, so everything is moved to the right side 2 units. Here's a subtraction. Okay, this is one example. In order to get it, how do I get it? I just shift it right 2 units. Okay. If you get the other point, you can get higher and to make them identical. But here we just see the idea. Okay, so when you subtract 4, you will see you shift it to the right. 2. You subtract 2 from x, you shift it to the right. And we can do the similar example. Fx is x squared. Gx is x plus 2 squared. Then let's check this a similar graph. We just want to confirm the left shift motion is corresponding to the plus 2. 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, we need this 9. Okay, so for f, let's check at 0, 0. Okay, so f negative 3 is 9, f of negative 2 is 4, f of negative 1 is 1, f of 0 is 0, f of 1 is 1, f of 2 is 4, f of 3 is 9. Okay, so this is 0, 0, 1, 1, negative 1, 1, 2, 4, negative 2, 4, 3, 9, negative 3, 9. So we use dotted line to demonstrate my point is bad, so demonstrate the graph of f. And then let's check a graph of g. Graph of g, let's use several different points. So one x is 1, g of 1, 1 plus 3, 1 plus 2 is 3, 3 squared is 9. G of 0, 0 plus 2 is 2, 2 squared is 4. G of negative 1, negative 1 plus 2 is 1, 1 squared is 1. G of negative 2, G of negative 2 plus 2 is 0, 0 squared is 0. G of negative 3, negative 3 plus 1, 2 is negative 1, negative 1 squared is 1. G of negative 4, negative 4 plus 2 is negative 2, squared is 4. G of negative 5, negative 5 plus 2 is negative 3, squared is 9. So 1, negative 1, negative 2, negative 3, negative 4, negative 5. Okay, negative 5 is 9. Negative 4 is 4. Negative 3 is 1. Negative 2 is 0. Negative 1 is 1. Negative 0 is 0 is a 4. 1 is a 9. So see, well, assume my sketch is correct. You see here, you exactly shift horizontally left 2 units. You shifted the original graph horizontally left 2 units to get the new graph. See, that's exactly the same thing. I choose a different sample point because for the different sample point you will see the parallel corresponding values. So, okay, so from these two examples we get the shift of the horizontal shift. Okay, so what is the horizontal shift? The conclusion. The conclusions. The conclusions are following. It's on page 246. If the argument input, they use different word. Argument is input is x. If the argument x of a function f is replaced by x minus h, h positive. The graph of the new function of a new function y equal to fx minus h is the graph of f shifted horizontally minus to the right. Horizontally right h units. Okay? You minus it. You see here, you minus it. You have to use a large value of x to reproduce the original quantity. Minus 2. When x is 2, it behaves like 0 in the original function. So you have to move to the right to get a bigger input. And this is a subtraction right. And be careful, this is x is totally replaced by x minus h. Okay, so for example, if your function is x squared plus x, then your fx minus h becomes x minus h squared plus x minus h. You have to replace all x by x minus h. It's not just first term or some special term. Everything, all the x term should be replaced by x minus h. So that's very important. Don't just replace one term. Add all the terms. Okay, so this is a subtraction right. And let's see the counterpart. If the argument x of a function f is replaced by x plus h, here again h is positive, the graph of the new function y equal to fx plus h is the graph of f shifted horizontally left h units. When you get f of x plus h, you shift the graph horizontally left h unit. It's like this one. You add h already, so when you have a smaller input with this h, it becomes bigger. So you get some support. So you can achieve some value when input is small. So that's why you shift it to the left. Okay. Okay, so the first two conclusions, we discussed two conclusions already. The first two conclusions are not four conclusions technically, but two big classes of conclusions. Those conclusions are about horizontal shift and the vertical shift. Of course, we can mix them, combine the vertical shift and the horizontal shift, okay? So graph the function fx equal to x plus 3 squared minus 5. Okay, so how do we do that? We first start from fx equal to x squared. Fx equal to x squared, and then you see x plus 3, so we want to get fx gx equal to let's still use the name fx equal to x plus 3 squared plus 3. You shift it horizontally to the left, so everything you shift to the left 3 unit. The 0 is moved to negative 3. 1 is moved to negative 2. 2 is moved to negative 1. And the negative 1 is moved to negative 4. Negative 2 is moved to negative 5. Okay, so this is a horizontal shift. You just parallelly move it to left. And then subtract 5. 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4, 5. When you get 0, here is 0. You subtract 5 means you shift the graph vertically down 5 units. You have 0. You shift it 5 units down. You see 1, 2, 3, 4, 5 is 5 here. We'll get 1, you shift 5 units down, it's negative 4. We'll get 4, you shift 5 units down, it's negative 1. And similar thing. So that's a graph x plus 3 squared and minus 5. Okay, so you first do the horizontal shift, and second you do the vertical shift. Right? And in this part, it's in this example, I just say in this example, if you just combine the horizontal and the vertical shift, you can first do the vertical shift and then do the horizontal shift. It's the same thing. We can do it here. This is a horizontal plus vertical. Now let's try a different way. We start first from this graph. 1, 2, 3, 4. So this is fx equal to x squared. If this is this order. Now let's try. We shift 5 units down. 0 is shifted to negative 5. 1 is negative 4. 4 is negative 1. Okay, that's the first part. And second, you're going to shift it to the left 3 units. One, 2, 3, 4, 5. 1, 2, 3, 4, 5. So 2 shift 3 unit left is negative 1. Its unit is here. It's negative 1. And 1 is shifted to, you see, 3 unit. 1, 2, 3 is negative 2. This is also moved 3 unit. 1, 2, 1, 2, 3. So it's a negative 4. It's here. And the 0 is shifted to negative 3. It's here. And here and here. Just get the same precise label and shift it to the left unit, left 3 unit. So you see here, these two graphs are identical. So I try to emphasize here, if there are only vertical and horizontal shifts, the order does not matter. The order does not matter. Okay? Okay. Fine. Now let's talk about another type of transformation, compression and stretch. What is compression and stretches? So the example, we use example to start the argument. So use the graph of fx equal to upside of x to obtain the graph of g of x equal to 2 times upside of x. Multiply this input by 2. Multiply the argument by 2. Okay? Or multiply the function, not argument, sorry. Multiply the function by 2. This is one function directly multiplied by 2. Not argument, function. Okay, so we multiply the function by 2. Let's check what is happening. Okay, this is the graph of upside of x. The graph of upside of x. And if we multiply it by 2, so when you get 1, upside of 1 is 1 times 2 is 2. You got here. When you get 2, this upside of 2 is 2. 2 times 2 is 4. It's here. So if you sketch it, it will be like this. And for the negative part, it's similar. But they're both straight line. Okay, so after you multiply it by you multiply the function by a greater number, by a greater positive number greater than 1, then you make it thin. Okay, or we call it a vertical stretch. vertically stretched. Okay. Let's change the coefficient. Use the graph of fx equal to upside of x to obtain the graph of g of x equal to 1/2 upside of x. G of x 1/2 upside of x. Let's do the similar stuff. 1, 2, 3, 4. 1, 2, 3, 4. 2, 3, 4. Let's use the diagonal. The other diagonal, it's a upside of x. And when multiplied by 1/2, for example, 1x is 1, upside of 1 is 1 times 1/2 is 1/2 is here. 1x is 2, upside of 2 is 2, 2 times 1/2 is 1. It's much more flat. When x is 3, you will get 3/2. When x is 4, you will get 2. You will get 2. So if you do the proper sketch, you will get these two more flat straight segments. Okay, so this is 1/2 upside of x. This one is 2 upside of x. Okay, so it's called vertically compressed. It is vertically compressed because the coefficient is less than 1. We'll talk about positive number. The coefficient less than 1. It's vertically stretched because the coefficient is greater than 1. Okay, so after those two examples, let's get our conclusion. This is our conclusion 5 and 6. Conclusions is on page 248. So when the right side of a function y equal to fx is multiplied by a positive number, A, the graph of the new function y equal to A times fx. A is the coefficient of the whole function. It doesn't matter how many terms you have to multiply each term by A when I say the addition subtraction. So this is a coefficient for everything. Is obtained by multiplying each y coordinate on the graph of y equal to fx. by a. So whenever you have a y coordinate, you just multiply itself by this coefficient a. Okay, then that's a rule, but basically that's just how you evaluate. Then the next sentence, the new graph is a vertically compressed here for a between 0 and 1, or a vertically stretched if a is greater than 1 version, compressed version or stretched version of the graph of y equal to fx. So the next sentence, the second sentence, is actually just a name, how we call it. If a is between 0 and 1, we call it vertically compressed. If a is greater than 1, we call it vertically stretched. Okay, that's just a name. It's just a name. We multiply this. We multiply this whole thing by a. We do the vertical stuff because you see here, this a actually is related to y. This a is related to y. And what happens if we multiply or we affect the argument x? What happens if we just directly operate on x? This is actually the operation on y. So you do the y coordinates. What happens if the argument x of a function y equal to fx is multiplied by a positive number a? Okay, so we are talking about this one. What happens? The following thing is the argument, is a conclusion. We will first, let me see the time. Okay, let's leave this for the next video. My video usually just take like 55 minutes. I cannot finish it in 7 minutes. So I will answer this question in the second video. We talk about the rule, a conclusion if we multiply the argument by a coefficient a. Okay, so we finish this video and start next video to explain.